We were talking about the Moore-Penrose pseudo-inverse. We have talked about the theorems which are available, what is the interpretation of this type of inverse, and then we stop by a few theorems. So one of the other theorems that we need to know is given A to be an Rm by n, and the two orthogonal matrices of V U to be n by n and V to be an n by n, then UAV plus will be V transpose A plus U transpose. So if we have A and two orthogonal of R n by n and n by n, if we are calculating the inverse, this is how we can calculate the inverse. In order to prove this theorem, you should check all property 1 to property 4. You know, AGA is equal to A, GAG is equal to G, then AG is A and GA is also A. No, AG is I and GA is also I. You have to check that if this term, whole term is RA and this whole term is RG, then those properties are satisfied. This is actually a very useful theorem because today we will start the next chapter, which is talking about the singular value decomposition. And you will see that we have this term in the singular value decomposition as well. One note that you may remember, if A is a diagonal matrix, okay, if A is a diagonal matrix whose and when we say diagonal matrix means that only elements of diagonal are number, the rest are definitely zero. Why I use the term number? Because this number can be zero, but definitely of the diagonals are zero. What is its inverse?
It should be another number.
If you a diagonal, but each element of the diagonal is 1 over of the previous values. And if one of these elements is zero, what is the result? Well, because it's undefined, we calculate the pseudo-inverse. So what is the inverse of 0? The pseudo-inverse of 0?
1?
0.
0.
Pseudo-inverse of 0 is 0. So we remember that one also. Now, let's have another theorem. So the theorems like this, which I said that can't be proved, if you need to know the proof, it's easy to prove. Some of them they are available in the book. But if I don't prove it, don't tell you that the proof is important, you don't need to know it. For A belonging to, again, R n by n, then we have two terms. A plus is A transpose A plus multiplied by A transpose, which is A transpose multiplied by A transpose plus. And number 2, which is very useful, is A transpose plus is equal to A plus transpose. In other words, the transpose and the plus, we can check it. And the proof is available in the book. On page 31 of the book, you can see the proof. Please note that in general, A multiplied by B plus is not B plus multiplied by A plus. We know that if we have the inverse of the matrices, we know if S squared matrices P and Q are non-singular, then P, Q inverse is Q inverse multiplied by P inverse. We know that one. But in general, when we are talking about pseudo inverse, this is not true. And we can always go over an example. Given that A is zero, 1, and B is 1, 1, then AB, what is AB? What is this result of multiplication?
1.
1. So, what is the inverse of A? 1? Is 1 itself. Whereas B plus will be this matrix, and A plus is this matrix, and B plus A plus is equal to 1 over 2. So we can see that AB plus is not equal to B plus A plus. However, although AB plus is not B plus A plus, but we have a theorem which says that AB plus is equal to pseudo inverse of B1 multiplied by pseudo inverse of A1, where B1 and A1 is defined to be A plus AB, and A1 is A, B1, B1 plus. So in order to calculate A1, we need to know B1, because we are using B1 in order to calculate the A1. We have also a small theorem. If R belongs to n by R with the rank of R, and B belongs to R by n of rank R, then here AB plus is equal to B plus else. Note, what is the pseudo-inverse of pseudo-inverse of A? What is the pseudo-inverse of pseudo-inverse of A?
Approximated.
It is A. What is the range of A plus? If you do the same as the range of A transpose?
N?
Range of space. You don't know you don't remember the range of space? And then null space is the null space of AT. If the matrix A is normal, then we can say that we can interchange A to power k multiplied by A, pseudo-inverse of A with pseudo-inverse of A by A to power k. And A pseudo-inverse to power k is equal to A to power k pseudo-inverse. What does it mean if A is normal? It means that if A belongs to R n by n, A transpose is equal to A transpose A. So you can see there exist many theorems which are kind of an alibi theorem. We just need to know what are the consequences. And some of these theorems we will use them in the next steps of this course. Like the first theorem that I wrote, we will see today when we are talking about the singular value decomposition. But before we proceed, we will have our next set of homework. Question 2. Question 5 and question 6. So another 3 questions. 2, 5, and 6. So this is our fourth homework, right? How many of the homeworks have reached the deadline? 2 of them, right?
Almost. Just one.
Just one. Now, if you remember when I was talking about this pseudo-inverse, I said many computer languages like MATLAB, when they want to calculate the pseudo-inverse, which is called an approximation, they are using a method which is called singular value decomposition. Now today we will start a new chapter which is talking about this singular value decomposition. We will see how the singular value decomposition works. Different books have different lecture notes have different approaches to get to this singular value decomposition. The book that we are following, it talks about the singular value decomposition. Later it will go and talk about the IN values and IN space stuff. Many other books, when we are looking at them, they actually use the IN values. They talk about IN values, and later they will go to the singular value decomposition. I also prefer to talk about singular value decomposition now because these pseudo-inverse and linear, this singular value decomposition are very much tied to each other. Because in order to calculate, let's say, pseudo-inverse, we really need to know the singular value decompositions. Now, what happens is that when today we will start to talk about the singular value decomposition, we will not finish it. In the next lecture, I will solve an example that we will use the singular value decomposition in order to find the inverse of the matrix. Of course, we can do it on paper when we are getting the small sizes. When we have the big sizes, then we need to really have a computer. So our title of today's talk is mainly singular value decomposition. It is what we use in many fields of computer science. Let's start with the definition. A matrix A is called positive. Definite if for any x belonging to Rn, x transpose Ax is positive. We want to talk about singular value decomposition, so we need to define also what are singular values. Singular values are a square roots of. Do you remember the term eigenvalue from undergraduate algebra? We will get back to this definition of eigenvalue later, but it's good to revise it in order to remember what it was. Singular values are the square roots of eigenvalues of A transpose A. So eigenvalues, check what they are, but we will talk about them in details in a couple of weeks. So we will get back to these topics shortly. So we know what is the meaning of the singular value. Let's write a theorem to see what is singular value decomposition. The theorem says, given A to be R, M, N with the rank R, then there exists matrices U belonging to R m by n and V belonging to R n by n, that A can be written as U sigma V transpose as a multiplication of this. Where sigma is a block matrix. That's why I write the zeros big. And S is a diagonal matrix whose diagonal values are sigmas, and the sigmas we mean are singular values. What is the index here? R. So S belongs to RR. And apart from sigma being a diagonal, look, we can write it as a diagonal matrix, whose some part of that one is singular values, sigma 1, sigma 2, sigma n, r. We have this property, sigma 1 is greater equal than sigma 2 is greater equal than till sigma r. So they are all sorted. So this is r by r. Can you tell me now what is the size of this 0? Because if you put them on top of each other, it should be column should be r. But what about the rows?
M.
The total should be m. So it will be m minus r.
Okay.
Because m minus r plus r, it should make m. What about these zeros? Definitely we have r columns and r rows or m minus r rows in here.
And n.
N minus r.
Okay. And
Because the total should be n.
R.
And this one is also r by n minus r. So similar values, which we know are the iron value of A transpose A, are here. Now we will see what they are representing, how we can use them in order to interpret some stuff. Because in general, if we have the rank R, we notice that if we have the rank R, S will have the size of R by R. So we can write A to be U1, U2 multiplied by S0, 0, 0, V1 prime, V2 prime. So in other words, my U, I can divide it into two parts, right? I can divide it into two parts. Can you tell me what is the size of U1? It will be M by R. Why R? Because R is the rank. So I want to divide it into based on the rank. So accordingly, you can guess what is U2, you can guess what is V1, and what is V2. So if we do the multiplication, look look what is happening. Right. Look what is happening. If I multiply this one with this, what do I get? U1 S1. What will happen to U2? 0. In here,
0.
I will get zeros. And then if I multiply the results, what happens is that I will get U1 SV1 transverse. So from here, I can get this conclusion. What is rank of a matrix? From all these things that I have written, what can be understood about the rank of a matrix? Is number of non-zero singular values. Look. Rank, someone look.
Yeah.
Rank R is number of elements that I have in the S. Right? Why? Can any of these come to be 0? No, because if it is 0, I will put it here. So, how many elements I have, how many non-zero singular values I have, it tells me that how many, what is the rank. For a matrix A, the ratio of the biggest singular value over the smallest singular value will result into something which we call a condition number. Will result into something which is called a condition number. And we show it with kappa. Okay, so it is sigma 1 divided by, can you tell me what is the index? We know that the biggest one is sigma 1. Why? Why the biggest one is sigma 1? Abdullah, this is why the biggest one is sigma 1? Not sigma 2?
Because from the purpose of it, it's
yeah, because it's already sorted. So sigma 1 is the biggest. So what is the smallest one?
sigma r.
Sigma r. Excellent. Because the rank is r, and we know that the last non-zero singular value is sigma r. Now, this is actually calculated in this form. This is actually calculated in this form. So what I write from here, we might get back to them a bit later. I can write it as sigma 1 multiplied by 1 over sigma r. The biggest IN value, is the second norm of the matrix. Let me write it first. The biggest, largest singular value is the second norm of the matrix. In other words, second norm of A is equal to sigma 1. So it means that instead of this one, I can write norm of A. Right? In order to continue this, I have to write down some other parts. I want to jump to this part of the board and ask you a question. Do you remember the first theorem that I wrote today, where it says that A plus is U1 S B1 transpose plus, which will be V1 transpose S, sorry, V1 transpose S plus U1 transpose. Now, S is diagonal. What is the size of S? R by R. Look, S is R by R. We have killed all the zeros. What is the determinant of S?
1 over.
The determinant of S is the multiplication of all the diagonal elements. And we know that we don't care about the number. It is not 0. So it means it is inversible. So what is the S plus?
1 by S.
It's S inverse.
S inverse. Yeah.
Okay? It is S inverse. Now, can you tell me that if I am calculating, or let's put it in this form. This is diagonal, right? This is diagonal. Inverse is also diagonal. Can you tell me that what is the biggest number in here in S inverse?
The sigma R.
Sigma R. No, well, don't call it sigma R. The last element.
Last element.
Biggest value is the last element. What is it? Which is?
1 by sigma R.
1 divided by sigma R. Because we know that if sigma 1 is greater than sigma R, the reciprocal of this one, the direction will change. So 1 over sigma 1 is the smallest, 1 over sigma R. Do you agree with this? So 1 over sigma 1 is the biggest singular value of which matrix? This matrix. And in case of our situation, this is the second norm of A inverse. This part is only for your information. In order to calculate kappa, kappa is very important when we do a numerical example, and you see why I'm talking about this condition number. Condition number. What do we mean by condition? And in order to calculate it, you do not necessarily need to go to use your computer to calculate singular value decomposition. Someone is using singular value decomposition, and he knows that how much time it takes in the computer if you have a big matrix to calculate it. So here, I don't care about the other singular values. What I care is sigma 1 and reciprocal of sigma R. So I can calculate A and A inverse, and I can look at the second norm. Now, another important thing about kappa is, what can you tell me about kappa? What is the smallest number that kappa can have? Fatima? 1. The smallest number is that all the sigmas are the same, so sigma 1 and sigma are the same, so the result is minimum 1. So kappa is always greater or equal than 1. So let's see what we mean by condition. the condition number is indicating how much change on the input of function or operator. We know that the matrix is an operator, right? Or a function which takes us from V vector space to W vector space, from a domain to codomain. How much change on the input of the function operator can affect on the output. Let me see if I put it in the correct form. How much change or a small change on the input can affect on the output. In other words, if I change my input a little bit, what will happen to the output? You know that we have systems that they are very stable systems. I'm talking about control. And you hit it, it gets back to its position. So it's pretty stable. In other words, even if you apply a big input, which has a high impact, you have a slight change of output. And there exists some system, like a pyramid, which you put it on its end. So if air blows, it will fall down. Right? So a very small change can make huge changes. So this condition number will tell us about this effect. Good. So if I know this number, then it means that if kappa is a small number, then A is called a well-conditioned matrix or operator or function. What does it mean, well-conditioned? Well-conditioned matrix. It means, you can read it in this way. The column vectors of A are well linearly independent. They are very, very linearly independent. In other words, with one look, you can say, oh, there is no way that they are depending on each other. Like the bases, 1, 0, 0, 0, 1, 0, or 0, 0, 1. So you look at it and you say that it's not possible to create one with the other one.
So it's also KD when where is that KD minimum value of K is 1.
Yes.
Also
10 and compared with 1000. So 10 is very small. So by small, I don't mean 0.001. If K is small. So this is an adjective, and usually you need to have two values in order to compare. So K is small, it means that we are well conditioned. So what is the second situation? If kappa is a big or large number, then A is called, what is it called, Lina? An ill condition. Matrix or operator. And what do I mean by ill condition? Column vectors of A are close to be linearly independent. are close to be linearly dependent. Read in this form. A is close to be singular. It's not singular, but it's very close to be singular. Like you calculate the determinant, and the determinant will be, let's say, 0.001. So very close to be 0. Do you know what will happen if the determinant is very close to 0? Close to singular. It means that the probability of making error in calculation of A inverse is high. Now, I have a numerical example. I have a numerical example in which we will calculate kappa and we see what is the situation, what we mean by well condition and what we mean by ill condition. And the example, the numerical example is this. Imagine the result of some experiments has led into the following equations. A is equal to B, where A is there anyone with the computer who has MATLAB? Others, do you have it?
Yes.
I want you do you have MATLAB? Oh, okay. Okay, if you take time, so. If we have MATLAB, I forgot to write the numbers, but if we calculate the similar values and you calculate kappa, you will see that the result is a big number, which means that this is an ill condition. Let's see what we mean by ill condition. Again, if you use your MATLAB to solve this system of equation, you will get x1, x2, x3 to be 0.5, 0.8, and 0.7. Now, I want to solve this one again. And this is my A. Did it open? Did it open? Oh, okay, still thinking. Good. You have to be faster than this in the exam. So, in condition, or the big value of kappa meant that if we change the input slightly, the output will be changed significantly. So, we have this set-sum equation, we have got the result. So, this is the inputs, and these are the outputs. We have got the outputs. Look what I want to do with the input. I want to solve it very fast, and I don't have a computer, so I need to use pen and paper. So what I do, I round these numbers into 34.7, 70.9, and 82.9. I mean, the changes are a matter of some hundreds or thousands. Okay? And if you do it, and if you calculate the value for your x1, x2, and x3, you will get these numbers. Minus 1.68294, 8.92282, minus 3.5054. Observation. Slight change in the input has caused significant change in the results. So this is the meaning of the if condition. It didn't open, right?
Actually, I'm also connected to VPN.
Ah, okay. They're usually legal.
Yeah.
Problems. And the licensed ones needs to have the VPN because it will be university, right? Anyway, we don't need to calculate it. At home, calculate, do these things. Define, for example, USB to be SVD of your A. You all know how to define A in MATLAB. So write that one, and then do this. K is equal to S11 divided by S33. And look at the result. And you see the result will be big number, which means that we have a very in condition, which means that very slight changes results in totally different numbers. Do you have any question? Okay, if you have no question, this is the end of the lecture for today.